41 light-years from Earth, there's a world where rocks don't just melt, they vaporize. Where the surface glows brighter than molten steel. Where an entire year passes in less time than it takes you to sleep through the night. This is 55 Cancri A, and according to everything we thought we knew about planetary science, it shouldn't have an atmosphere. It shouldn't be able to hold on to gases at all. Yet somehow, against every prediction, it does. The discovery announced in May 2024 changed the game completely. Let's start with something that sounds impossible. Imagine a planet twice the size of Earth, but 8 times heavier. Now place it so close to its star that it completes an orbit in just 17.7 hours. The planet's surface temperature reaches 3,770 Kelvin on the side facing the star. That's 6,330 degrees Fahrenheit. Hot enough to turn silicon, iron, aluminum, and calcium into vapor. The night side, perpetually locked in darkness, still glows at temperatures exceeding 2,000 degrees Fahrenheit. This isn't science fiction. This is 55 Cancri A, officially named Janssen, and it represents one of the most extreme environments ever confirmed to exist. The planet orbits a sun-like star designated 55 Cancri A, located in the constellation Cancer. When astronomers first detected it using data from 2003 and 2004, they had no idea what they'd found. At the time of its announcement in 2004, Janssen became the first super-Earth ever discovered around a main sequence star. Nothing in our solar system prepared us for this. We have rocky planets like Earth and Mars. We have gas giants like Jupiter and Saturn. But we have nothing that bridges the gap quite like this, a world that defies our categories and challenges our models of how planets form and survive. The numbers tell a story of extremes that push physics to its limits. Janssen orbits at just 1.4 million miles from its host star. To put that in perspective, Mercury, the closest planet to our Sun, orbits at roughly 36 million miles. Janssen is 25 times closer to its star than Mercury is to ours. At this distance, the gravitational forces and radiation levels would absolutely devastate any world in our solar system. What happens to a planet in such proximity? It becomes tidally locked. One hemisphere eternally faces the star, baking under relentless radiation. The other faces the void of space, never seeing direct starlight. This creates a planetary environment unlike anything we experience on Earth, a world split between fire and relative cold, though even that cold side maintains temperatures that would instantly incinerate any known form of life. Early observations using the Spitzer Space Telescope between June and July of 2013 revealed something strange. The hottest spot on the planet wasn't where it should be. On a tidally locked world with no atmosphere, you'd expect the point directly facing the star, the substellar point, to be the hottest location. But measurements showed the peak temperature shifted 30 to 41 degrees eastward from where physics said it should be. Something was moving heat around. But what? Scientists initially proposed 2 possibilities. Either the planet had an atmosphere capable of redistributing thermal energy through winds, or something else entirely was at work, perhaps exotic rotational dynamics or internal heat transport through the planet's presumed magma ocean. For years, the debate remained unresolved. Spitzer's instruments, though revolutionary for their time, couldn't provide the spectral resolution needed to definitively answer the question. Then came the James Webb Space Telescope. Between its near-infrared camera and mid-infrared instrument, Webb possessed capabilities that transformed exoplanet science. In observations that each lasted about 8 hours, the telescope measured subtle changes in infrared light as Janssen orbited its star. The technique, called secondary eclipse spectroscopy, works by capturing the combined light of the star and planet, then subtracting out the star's light alone when the planet passes behind it. What remains is the planet's own thermal emission, its heat signature, carrying information about atmospheric composition encoded in specific wavelengths. The precision required for these measurements is staggering. Jansen's thermal emission is utterly dwarfed by the brightness of its host star. Isolating that faint planetary signal demands not just sensitive instruments, but sophisticated data analysis techniques that can tease apart overlapping spectral features. Multiple observations were necessary to build sufficient signal-to-noise ratios and check for consistency. When the team analyzed the data, they found patterns that shouldn't exist. Between 4 and 5 microns in the infrared spectrum, less light reached the telescope than expected. This dip, this absorption feature, pointed to something specific: molecules in the planet's atmosphere absorbing those particular wavelengths. The spectral signature matched carbon dioxide or carbon monoxide. Not vaporized rock, which would show a completely different pattern, but actual volatile gases. The kind of atmosphere you'd associate with volcanic outgassing, not a bare molten surface. This was the moment everything changed. For decades, atmospheric scientists operated under a firm assumption: rocky planets orbiting this close to their stars simply cannot maintain atmospheres. The physics seemed straightforward. Intense stellar radiation should strip away gases through atmospheric escape, where high-energy photons give molecules enough kinetic energy to overcome the planet's gravity and flee into space. At Jansen's orbital distance, this process should be devastating and continuous. Yet here was evidence, the strongest to date, that a rocky exoplanet beyond our solar system possesses a genuine atmosphere. Not rock vapor. Not a tenuous envelope of evaporated minerals. An actual secondary atmosphere, likely rich in carbon-bearing molecules, persisting despite conditions that should obliterate it. The discovery paper, published in Nature in May 2024, was unequivocal. The measurements ruled out the hypothesis that Jansen is simply a lava world shrouded in vaporized rock. Instead, the data indicated what researchers call the bona fide volatile atmosphere, one that's continuously replenished by outgassing from below. This is where the magma ocean hypothesis enters the picture. Scientists believe Jansen's interior remains so hot that vast portions of its mantle exist in a molten state. Temperatures and pressures keep enormous quantities of rock liquefied. As this magma ocean churns through convection, driven by the extreme temperature gradient between day and night hemispheres, dissolved gases bubble up and escape through volcanic activity. Think of it like champagne releasing carbon dioxide, but on a planetary scale with molten rock instead of wine. The outgassing rate apparently matches or exceeds the rate of atmospheric loss to space, creating a dynamic equilibrium. Gases escape. More gases bubble up. The atmosphere persists not because it's stable, but because it's continuously renewed, a planetary system maintaining itself against impossible odds through sheer volcanic vigor. Renyu Hu, a planetary scientist at the California Institute of Technology, pointed out something profound about this discovery. By observing this extrasolar example of atmosphere magma interaction, we gain insights into how the early solar system worked. Earth itself, during the first 100 million years after formation, would have been hot enough to maintain widespread magma oceans. Venus likely experienced similar conditions. Mars too. Studying Jansen gives us a window into processes that shaped our own world billions of years ago, except we're watching them unfold in real time rather than trying to reconstruct them from ancient geological records. The implications extend far beyond one peculiar planet. If rocky worlds can maintain atmospheres under such extreme conditions, what does that mean for our understanding of planetary habitability? What does it tell us about the diversity of rocky planet evolution? The conventional wisdom just took a serious hit, and scientists are racing to understand the mechanisms that make this possible. But there's more to this story. The controversy surrounding Jansen's very existence reveals how challenging exoplanet science can be, and how easily initial observations can mislead us. When astronomers first analyzed the radial velocity data that revealed Jansen's presence, they thought they'd found a planet with a 2.8-day orbital period. This measurement stood for years, shaping early models of the 55 Cancri system. Then in 2005, researcher Jack Wisdom questioned the planet's existence entirely, suggesting the signal was an alias, a false pattern created by the way the data was sampled. The debate intensified. Some analyses seemed to confirm the 2.8-day planet. Others cast doubt. Finally, in 2010, researchers Dawson and Fabrici demonstrated conclusively that the true orbital period was 0.7365 days. Not 2.8 days. Less than 18 hours. The planet was real, but it was far closer to its star than anyone had imagined. This correction wasn't just a minor adjustment. It fundamentally transformed our understanding of Jansen's environment, moving it from merely very close to extraordinarily close, from extreme to apocalyptic. When the planet's transit across its host star was finally observed and confirmed in April 2011 using the MOST Space Telescope, it vindicated Dawson and Fabrici's work and opened the door to direct characterization of the planet's properties. Transit observations are crucial because they let astronomers measure a planet's radius directly by watching how much starlight it blocks. Combined with mass measurements from radial velocity data, this enables calculation of density, a fundamental clue about internal composition. For Jansen, the density measurements revealed a world unlike anything in our solar system, setting the stage for decades of follow-up observations that would culminate in the James Webb Space Telescope's groundbreaking atmospheric detection. Now we understand that Jansen represents something extraordinary, a natural laboratory where planetary science meets its most extreme test case. The discovery of its atmosphere forces us to reconsider fundamental assumptions about what's possible in the universe. And the story of how we came to understand this world reveals the messy, contentious, ultimately triumphant process of scientific discovery itself. What we're learning is that the universe doesn't care about our assumptions. It will create worlds we never imagined, operating under conditions we thought impossible. Jansen is just the beginning. The temperature measurements tell a story that defies intuition. Jansen's dayside reaches 3700 Kelvin according to the latest Spitzer data reanalysis from 2022. That's 6300 degrees Fahrenheit. Hot enough to vaporize calcium. Silicon boils at these temperatures. Iron exists as vapor, not metal. We're not talking about a place where rocks melt, we're describing conditions where the distinction between solid, liquid, and gas becomes almost meaningless for materials we think of as permanent. The night side presents its own puzzle. Even though this hemisphere never sees direct starlight, it maintains temperatures around 1400 Kelvin. That's 2000 degrees Fahrenheit. Glowing red-hot in perpetual darkness. Something is redistributing heat across this world with remarkable efficiency, and for years scientists couldn't agree on what that something was. Here's where things get genuinely strange. When the Spitzer Space Telescope mapped Jansen's thermal emissions between June and July 2013, astronomers expected the hottest spot to align with the substellar point, the location directly facing the star. Basic physics suggested that's where maximum heating should occur. Instead, they found the temperature peak offset by 30 to 41 degrees eastward. 30 degrees doesn't sound dramatic until you realize what it implies. That offset means heat is being transported across the planet's surface through some active mechanism. Atmospheric winds could explain this. But so could more exotic phenomena involving the planet's rotation or internal dynamics. The offset is too large to dismiss as measurement error, yet too consistent to be random variation. Think about what this redistribution requires. You need energy transport powerful enough to shift the thermal maximum across hundreds of kilometers of surface. On Earth, our atmosphere and oceans accomplish this through convection and circulation patterns. But Jansen's environment is so extreme that conventional atmospheric models struggle to explain how gases could survive long enough to establish stable circulation. The debate raged for years. One camp argued the planet must have an atmosphere despite the hostile conditions. How else could you explain the heat distribution? The offset hotspot? The surprisingly moderate night-side temperatures? Another group countered that we were simply seeing vaporized rock, a tenuous shroud of silicon, iron, aluminum, and calcium boiled directly off the surface. At Jansen's temperatures, rocks don't just melt. They evaporate. This rock vapor could create something atmosphere-like without being a true secondary atmosphere. Distinguishing between these scenarios became crucial. A rock vapor envelope would form from the planet's own surface material, constantly replenished as long as temperatures stayed extreme. It's not really an atmosphere in the traditional sense, more like the haze above a boiling pot. A true secondary atmosphere would require ongoing volcanic outgassing from the interior, implying active geological processes in a fundamentally different planetary state. The Spitzer observations provided tantalizing clues but lacked the spectral resolution to definitively settle the question. Infrared brightness measurements showed patterns inconsistent with a bare rock surface, suggesting some kind of gaseous envelope. Yet the data couldn't identify specific molecular signatures that would prove the presence of volatile compounds like carbon dioxide or carbon monoxide. Scientists needed better instruments. They needed precision spectroscopy capable of detecting absorption features from specific molecules. They needed observations that could distinguish between the spectral signature of vaporized rock elements and actual atmospheric gases. Enter the James Webb Space Telescope. Webb's near-infrared camera and mid-infrared instrument can measure thermal emission spectra with unprecedented detail. The observing strategy was elegant. Watch Jansen complete multiple orbits, capturing data when the planet is visible beside its star and when it disappears behind the star during secondary eclipse. During eclipse, you're seeing only starlight. Before and after eclipse, you're seeing starlight plus the planet's own thermal glow. Subtract one from the other, and you isolate the planet's emission spectrum. Each observation session lasted about 8 hours, covering nearly half of Jansen's 17.7-hour orbital period. The precision required is extraordinary. The planet's thermal emission is utterly dwarfed by the star's brightness, like trying to detect a candle next to a searchlight. Multiple observations were necessary to build sufficient signal-to-noise ratio and verify consistency across different orbital phases. When the team analyzed Webb's NIRCan data in 2024, they saw something unmistakable. A dip in the spectrum between 4 and 5 microns. Less light reaching the telescope at these specific wavelengths. This wasn't random noise or instrumental artifact. This was absorption. Something in the planet's atmosphere was absorbing infrared light at wavelengths characteristic of carbon-bearing molecules. Aaron Belloruff from JPL explained the significance. That spectral dip suggests carbon monoxide or carbon dioxide, both of which absorb strongly in this wavelength range. The MIRI data extending from 5 to 12 microns confirmed the pattern. This wasn't vaporized rock. Silicon, iron, aluminum, and calcium would produce completely different spectral signatures. What Webb detected pointed unambiguously toward volatile compounds, gases you'd expect from volcanic emissions, not from evaporated surface material. The implications hit immediately. Jansen has a bona fide atmosphere. Not rock vapor. Not a temporary artifact of extreme heating. An actual secondary atmosphere, likely rich in carbon dioxide or carbon monoxide, probably both. Gases that had to come from somewhere, that had to be continuously replenished against the relentless stripping force of stellar radiation. This shouldn't work. Conventional planetary science said rocky planets this close to their stars couldn't maintain atmospheres. The radiation environment is too hostile. High-energy photons should give atmospheric molecules enough kinetic energy to escape the planet's gravity entirely. Atmospheric escape should strip away any gases within geologically short timescales. Yet here's Jansen, maintaining an atmosphere despite conditions that should make retention impossible. The answer lies beneath the surface. Renyu Hu from Caltech explained the likely mechanism. The atmosphere isn't primordial, it's a secondary atmosphere, constantly regenerated by outgassing from a magma ocean. Imagine the entire planetary mantle in a molten state. Temperatures and pressures high enough to keep vast quantities of rock liquid. As this magma churns and convects, dissolved gases bubble out, similar to carbon dioxide escaping from champagne. This outgassing process creates a dynamic equilibrium. Yes, the stellar wind strips atmosphere away, but volcanic emissions from the magma ocean replenish it at rates matching or exceeding the loss. It's not a stable atmosphere in the sense of Earth's, it's a constantly refreshed envelope of gas maintained by ongoing geological activity. The magma ocean model explains multiple observations simultaneously. The heat redistribution. Convection in the molten mantle transports thermal energy. The offset hotspot. Preferential outgassing on the dayside creates atmospheric circulation patterns. The nightside warmth. Heat from the interior prevents complete cooling even in permanent darkness. Computer simulations of Jansen's interior dynamics reveal fascinating complexity. Using surface temperature contrasts as boundary conditions, researchers modeled two-dimensional mantle convection under different climate scenarios. If the dayside hosts a full magma ocean while the nightside remains solid or only partially molten, large superplumes form on the day hemisphere. Hot material rises in massive upwellings. Cold material descends on the nightside, though without forming strong downwelling structures. In some simulations, the superplume shifts tens of degrees toward the terminator, the boundary between day and night. This asymmetric convection could drive preferential outgassing on one hemisphere, potentially creating atmospheric composition gradients between dayside and nightside. Different gases on different hemispheres. Chemical stratification driven by the extreme temperature gradient. What makes this discovery genuinely revolutionary isn't just confirming the atmosphere's existence. It's demonstrating that our understanding of planetary atmospheres was too narrow. We built theories based on solar system examples: Earth, Venus, Mars, the gas giants. None of those worlds experience conditions remotely like Jansen's. We assumed extrapolation would work. The universe just proved otherwise. Diana Dragomir from the University of New Mexico, who contributed to discovering Jansen's transits during her doctoral work, emphasized the broader implications. This challenges fundamental assumptions about what's possible. If rocky planets can maintain atmospheres under such punishment, what does that mean for planetary habitability elsewhere? What does it reveal about the diversity of rocky planet evolution? The magma ocean mechanism opens new questions. How common are lava worlds in the galaxy? Do other ultra-hot rocky planets maintain similar atmospheres? Could there be a whole class of worlds we've completely overlooked because we assumed atmospheric retention was impossible under extreme stellar radiation? Jansen gives us a window into processes that shaped Earth billions of years ago. Our planet spent its first 100 million years hot enough to maintain widespread magma oceans. Venus likely went through similar phases. Mars too. But we can't observe those ancient conditions directly, we're stuck reconstructing them from geological traces. Jansen lets us watch in real time, studying atmosphere-magma interactions as they happen rather than inferring them from billion-year-old rocks. The implications extend beyond theoretical interest in planetary science. Understanding how rocky planets retain atmospheres under extreme radiation could reshape our approach to finding habitable worlds. Current habitability models focus on moderate environments, Earth-like distances from Sun-like stars. But what if that framework is too conservative? Consider red dwarf stars. They make up roughly 70% of all stars in the galaxy. Most known exoplanets orbit red dwarfs. And red dwarfs present a problem. Their habitable zones, where liquid water could exist, sit uncomfortably close to the star. Close enough that stellar flares and radiation would seemingly strip away atmospheres. Conventional wisdom suggested rocky planets around red dwarfs couldn't maintain the atmospheric protection necessary for life. Jansen changes that calculation. If a world can hold on to an atmosphere while orbiting at 1/25 Mercury's distance from a Sun-like star, while enduring temperatures that vaporize rock, then maybe our assumptions about red dwarf habitability need revision. The mechanisms keeping Jansen's atmosphere intact might operate elsewhere. Different scales, different temperatures, but the same fundamental principle: continuous replenishment overcoming atmospheric loss. This doesn't make Jansen habitable. Nothing lives at 3,700 Kelvin. But it proves atmospheric retention works under conditions we thought impossible. And that matters when searching for life beyond Earth. The detection methods used for Jansen also demonstrate how far exoplanet characterization has advanced. Webb's instruments measured infrared light in the 4 to 12 micron range. Each 8-hour observation captured nearly half the planet's orbital period. The planet completes a full orbit in under 18 hours. That rapid orbit initially seemed like a disadvantage, less time for detailed observation. But it actually helps. Multiple orbits can be observed in a single observing session, allowing astronomers to build up signal strength and check for consistency. The secondary eclipse method Webb employed is deceptively simple in concept. Measure the combined light from star and planet. Wait until the planet passes behind the star. Measure just the star. Subtract. What remains is the planet's thermal emission. Simple in theory. Extraordinarily difficult in practice. The planet's contribution to total system brightness is minuscule. Like trying to detect a candle next to a searchlight from 41 light-years away. And not just detect it, measure its color spectrum precisely enough to identify specific molecules. Aaron Belorov from JPL pointed out the telltale signature, a dip in the spectrum between 4 and 5 microns. That's where carbon monoxide and carbon dioxide absorb infrared light. If the planet were surrounded by vaporized rock, silicon and iron compounds would create completely different absorption features. The spectrum doesn't match rock vapor. It matches volatile gases. This distinction matters because it confirms the magma ocean model over alternatives. Some researchers have proposed that Jansen might be a bare rock world with a thin envelope of evaporated surface material. Under that scenario, the planet would essentially be sweating rock vapor. Silicon, iron, aluminum, the elements that make up planetary crust, would evaporate from the day side and circulate before condensing on the night side. That could explain some observations but struggled to account for the heat redistribution patterns and the stability of the thermal emission over time. The volatile atmosphere model fits better. Carbon dioxide or carbon monoxide released from interior outgassing creates a genuine atmosphere, not just surface evaporation. This atmosphere can transport heat through winds and circulation patterns. It can maintain relatively stable composition despite continuous loss to space because volcanic activity keeps replenishing it. And it explains why the planet's thermal emission shows less variability than expected for a bare rock surface. But questions remain. The atmosphere's exact composition remains uncertain. Is it primarily carbon dioxide? Carbon monoxide? Some mixture? Do other gases contribute significantly? Nitrogen, sulfur compounds, even water vapor from the magma ocean? Webb's current observations can't fully resolve this. Future observations with longer integration times and coverage of additional wavelengths could narrow the possibilities. The planet's internal structure also invites speculation. Standard rocky planet models don't apply straightforwardly. At the temperatures and pressures inside Janssen, rock doesn't behave like rock on Earth. Phase diagrams, the charts showing which states of matter exist under different conditions, become exotic at these extremes. Materials that normally form solid minerals might exist as superionic phases, where some atoms remain locked in crystal lattices while others flow freely like liquids. Bizarre states of matter that laboratories can barely reproduce. Some research suggests Janssen might have a carbon-rich composition rather than the silicon and oxygen-dominated chemistry of Earth-like planets. The host star, 55 Cancri A, shows elevated carbon abundance in its spectrum. If the protoplanetary disk that formed the system was similarly carbon-rich, planets might have incorporated more carbon than typical solar system bodies. Under the extreme pressures in Janssen's interior, that carbon could crystallize into diamond. This sparked the diamond planet hypothesis, the idea that Janssen's mantle might contain diamond layers hundreds of kilometers thick. It's a tantalizing possibility. The temperatures and pressures are certainly sufficient. Pure carbon at those conditions would form diamond. Whether Janssen actually contains enough carbon, and whether it's distributed in ways that allow large-scale diamond formation, remains speculative. But the chemistry isn't impossible. Density measurements provide some constraints. Janssen is roughly 8 times Earth's mass and twice Earth's radius. That gives a density of about 7 grams per cubic centimeter, higher than Earth's average density of 5.5 grams per cubic centimeter. Higher density suggests either more iron in the core or a compressed structure from the planet's gravity. Or both. It doesn't definitively prove or disprove the diamond hypothesis, but it's consistent with various compositional models. The planet's thermal variability adds another layer of mystery. Observations show the planet's brightness changes over time, not just the expected variations as it orbits, but longer-term fluctuations that suggest surface conditions aren't static. One explanation invokes massive volcanic eruptions. Picture Mount St. Helens scaled up by factors of thousands. Eruptions violent enough to inject vast dust clouds into the atmosphere, temporarily blocking thermal emission and changing the planet's apparent brightness. When the dust settles or gets swept away by atmospheric winds, brightness returns to baseline. Alternatively, the variability might come from a gas torus co-orbiting with the planet. Similar to Jupiter's Io plasma torus, a donut-shaped cloud of charged particles surrounding Jupiter in Io's orbit. Io's intense volcanic activity feeds this torus. If Janssen experiences similarly vigorous outgassing, it could create a surrounding cloud of material that periodically obscures or enhances the planet's thermal signature as viewed from Earth. Both explanations require extreme levels of geological activity. But Janssen is extreme in every measurable way, so neither scenario seems implausible. Scientists have also searched for electromagnetic interactions between Janssen and its host star. The planet orbits so close that it sits deep within the star's magnetic field. Jupiter's moon Io creates a magnetic footprint on Jupiter through electromagnetic coupling. Charged particles from Io's volcanoes interact with Jupiter's magnetic field, generating radio emissions. Similar interactions might occur between Janssen and 55 Cancri A. Radio observations in 2011 looked for these signals. Nothing detected. Either the interactions don't occur at detectable strength, or the observation methods weren't sensitive enough. The null result also suggests Janssen might lack a strong intrinsic magnetic field. Earth's magnetic field is generated by convection in its liquid iron core. Janssen's interior temperatures might prevent the kind of convection needed for dynamo action. Or perhaps the magma ocean itself disrupts magnetic field generation. Without a protective magnetosphere, atmospheric loss to stellar wind should be even more severe. Yet the atmosphere persists. That persistence keeps circling back as the central puzzle. Everything about Janssen's environment should doom any atmosphere. The stellar radiation. The lack of magnetic protection. The intense gravitational forces from tidal locking. The evaporation driven by surface temperatures exceeding 3000 Kelvin. Yet there it is, carbon-bearing gases surrounding a world that shouldn't have them. The magma ocean mechanism explains how, but raises its own questions. How deep is the magma ocean? Does it cover the entire planet or just the day side? What's the composition of the molten material? Is it similar to Earth's mantle composition, or something more exotic? How efficiently does convection operate under these extreme conditions? And most intriguingly, does the night side have fundamentally different conditions that might create chemical gradients in the atmosphere? That last question touches on something particularly fascinating about tidally locked worlds. The permanent day and night hemispheres create environments so different they might as well be separate planets. One side continuously blasted by stellar radiation, the other side in eternal darkness. The atmospheric dynamics between these two faces would be extraordinary. If an atmosphere exists, and we now know it does, winds must connect the hemispheres. Heat from the day side gets transported toward the night side through atmospheric circulation. But how efficiently? That depends on wind speeds, atmospheric density, and the atmosphere's chemical makeup. Computer models of tidally locked planets suggest wind patterns unlike anything on Earth. Instead of the Coriolis-driven circulation cells we're familiar with, tidally locked worlds develop what's called a superrotating jet, a continuous high-altitude wind stream that flows eastward around the planet at tremendous speed. This jet would redistribute heat, carrying energy from the scorching day side toward the cooler night side. On Janssen, these winds might reach hundreds or even thousands of meters per second. Hypersonic winds sculpting temperature gradients that would be lethal in either direction. Standing on the day side would be like facing a blast furnace. Standing on the night side would still be hot enough to melt lead, but relatively speaking, comparatively mild. The terminator, the boundary between day and night, becomes the most interesting region. Here, conditions transition from one extreme to another. Temperature gradients drive powerful convection. Rising air from the day side meets descending air from the night side. Turbulence would be constant and violent. If life were ever to exist on such a world, and it can't on Janssen, but theoretically on cooler tidally locked planets, the terminator would be the only survivable zone. Not too hot, not too cold. Though on Janssen, even the terminator remains far above the boiling point of water. Computer simulations of Janssen's interior reveal mantle dynamics that would reshape our understanding of planetary geology. The extreme temperature difference between hemispheres creates asymmetric convection patterns. Hot magma rises on the day side, forming massive plumes. These aren't small volcanic features, they're continent-sized upwellings of molten rock pushing toward the surface. On the night side, cooler material descends. Though cooler is relative, it's still thousands of degrees. These descending flows complete the convection cell, driving circulation through the planet's mantle. The entire planet becomes a heat engine, powered by the temperature differential its tidal locking creates. The dayside plumes can shift position. In some models, they migrate tens of degrees toward the terminator. This movement would create varying volcanic activity across the dayside, with hotspots appearing and disappearing over time. If volcanic outgassing is concentrated in these plume regions, atmospheric composition might vary geographically. The atmosphere near the strongest plume would be richer in freshly outgassed volatiles. Regions away from active plumes would have older, more processed atmospheric chemistry. This brings up something fascinating about Janssen's atmosphere. It's not static, it's being constantly renewed. Every second, stellar radiation strips away gases on the dayside. High-energy photons and stellar wind particles collide with atmospheric molecules, giving them enough velocity to escape Janssen's gravity. The atmosphere bleeds into space continuously, yet it persists. The magma ocean replenishes what's lost. Dissolved gases in the molten rock bubble to the surface through volcanic vents. The same process that created Earth's early atmosphere 4 billion years ago continues on Janssen today. It's a dynamic equilibrium, loss balanced by supply. Remove either factor and the atmosphere would either grow indefinitely or disappear completely. This equilibrium is delicate. Small changes in volcanic activity or stellar radiation could tip the balance. If volcanic outgassing slows, atmospheric loss would gradually thin the atmosphere. If stellar activity increases during a flare, temporary atmospheric stripping could occur before volcanic replenishment catches up. The atmosphere's composition reflects this balance. Carbon dioxide and carbon monoxide dominate because they're stable enough to survive in this environment and abundant in volcanic emissions. Other gases present in smaller quantities might include sulfur dioxide, water vapor, and various rock-derived species. But the carbon-bearing molecules dominate the spectral signature Webb detected. Water deserves special attention. Earth's magma contains dissolved water that outgasses during eruptions. Janssen's magma ocean likely contains water too. But at dayside surface temperatures, water can't exist as liquid. It would immediately vaporize. Even on the night side, temperatures remain too high for liquid water. Any water in Janssen's atmosphere exists as superheated steam. This steam contributes to the greenhouse effect. Water vapor is an excellent absorber of infrared radiation. Even in small quantities, it would trap heat, contributing to the night side surprisingly high temperatures. The night side doesn't cool as much as bare rock calculations would suggest, partly because atmospheric circulation brings heat from the dayside, and partly because greenhouse gases trap what little heat remains. The vertical structure of Janssen's atmosphere adds another layer of complexity. Near the surface, the atmosphere is dense and hot. Pressure increases with depth into the magma ocean until there's no clear boundary between atmosphere and planet, just a gradual transition from gas to liquid to solid as you descend. Higher up, the atmosphere thins. Temperature remains high due to stellar radiation, but pressure drops. At some altitude, the atmosphere becomes thin enough that molecules can escape to space. This exosphere marks the fuzzy edge of Jansen's atmosphere, where the planet ends and space begins. Comparing Jansen to early Earth reveals profound connections. When Earth formed 4.5 billion years ago, the entire surface was molten. Impacts during planetary formation delivered enough energy to melt rock globally. The early Earth was a magma ocean world, probably tidally locked to the moon before tidal forces gradually slowed Earth's rotation. During this period, Earth's atmosphere came from volcanic outgassing. Carbon dioxide, water vapor, nitrogen, and other volcanic gases accumulated. The atmosphere was thick, hot, and utterly hostile to modern life. But it was the starting point for everything that followed. As Earth cooled, the magma ocean solidified. Water vapor condensed into oceans. Chemistry became more complex. Studying Jansen gives us a laboratory for understanding that crucial phase. We can't travel back 4 billion years, but we can observe a world currently in a state Earth once occupied. The processes happening on Jansen right now happened on Earth long ago. Magma ocean dynamics. Atmospheric outgassing. The balance between atmospheric creation and loss. Venus offers another comparison. Modern Venus has a crushing carbon dioxide atmosphere that creates a runaway greenhouse effect. Surface temperatures reach 750 Kelvin. But early Venus, like early Earth, was likely covered by magma oceans. Venus's atmosphere today is a product of billions of years of evolution, outgassing, atmospheric loss, and chemical reactions that eventually created the hellscape we observe now. Jansen represents an arrested state. Its proximity to its star prevents cooling. The magma ocean never solidifies. The planet remains locked in the early phase that Earth and Venus passed through. It's a living fossil of planetary evolution, preserved by extreme conditions that prevent further development. Mars provides a contrasting example. Mars once had a thicker atmosphere, probably sustained by volcanic activity. But Mars is small. Its interior cooled relatively quickly. Volcanic activity slowed and eventually stopped. Without replenishment, atmospheric loss gradually stripped away most of Mars's atmosphere. Solar wind and lack of a protective magnetic field accelerated the process. Jansen's size, 8 Earth masses, means its interior remains hot through radioactive decay and tidal heating. Volcanic activity will continue for billions of years. Unlike Mars, Jansen won't cool enough for atmospheric loss to win. The magma ocean persists, and with it, the atmospheric replenishment mechanism. These comparisons highlight how planetary outcomes depend on multiple factors. Size determines how long internal heat lasts. Distance from the star determines surface temperature and atmospheric loss rates. Rotation state affects heat distribution. Magnetic fields protect atmospheres from stellar wind. Chemical composition influences what gases are available for outgassing. Change any of these variables and you get a different world. Put Jansen farther from its star and it becomes a super-Earth with a solid surface and potentially habitable conditions. Shrink it to Mars size and it cools quickly, losing its atmosphere despite volcanic activity. Remove the magma ocean and the atmosphere disappears within thousands of years. Jansen occupies a precise point in this parameter space where extreme conditions create an unlikely equilibrium. The planet is large enough to stay geologically active, close enough to its star to maintain surface melting, tidally locked in a way that creates extreme hemispheric differences. And it has exactly the right composition to supply carbon-bearing gases through outgassing. Shift any factor slightly and Janssen would be something else entirely. It sits on a knife's edge between multiple possible states, maintained by the exact conditions it experiences. That precarious balance makes it scientifically invaluable. Understanding why Janssen's atmosphere survives teaches us about the boundaries of planetary habitability and the conditions necessary for atmospheres to persist. But there's something else Janssen reveals, something about the diversity of planetary outcomes in the universe. Before exoplanet discoveries began in the 1990s, our only examples were solar system worlds. We assumed other planetary systems would look similar. Rocky planets close to their stars. Gas giants farther out. Ice worlds at the edges. Janssen shatters that assumption. Super-Earths don't exist in our solar system. Tidally locked lava worlds weren't predicted by planetary formation models. The idea that a rocky planet could maintain an atmosphere while orbiting so close to its star contradicted theoretical expectations. Yet here it is. Real. Observed. Challenging us to expand our understanding of what planets can be. Every exoplanet discovery expands the catalog of known worlds, but some discoveries do more. They force us to reconsider fundamental assumptions about how planetary systems work. Janssen belongs to this second category. The 55 Cancri system contains multiple planets. Janssen orbits closest to the star, completing its circuit in less than 18 hours. Farther out are other worlds, Galileo, Brahe, Harriet, each occupying different orbital distances and exhibiting different characteristics. The system also includes a companion red dwarf star, 55 Cancri B, which hosts its own planets. This makes 55 Cancri one of the most populated planetary systems known outside our own. The architecture differs dramatically from our solar system. We have small rocky planets near the Sun, gas giants in the middle regions, and ice worlds at the outer edges. A clear pattern emerged from millions of years of gravitational sorting. 55 Cancri follows different rules. A super-Earth orbits where no planet should survive. Gas giants occupy unexpected positions. The whole arrangement challenges formation models based on solar system observations. Janssen's host star, 55 Cancri A, is a K-type star slightly cooler and smaller than our Sun. It's classified as Copernicus in the system's naming scheme, which honors historical astronomers and telescope pioneers. The star sits 41 light-years away in the constellation Cancer. Close enough that we can study it in detail. Far enough that we'll never visit. The star's composition matters for understanding Janssen. Spectroscopic analysis shows 55 Cancri A is relatively rich in heavy elements, particularly carbon. This chemical signature suggests the protoplanetary disk that formed the system contained higher proportions of carbon compounds than the disk that formed our solar system. That excess carbon might explain some of Janssen's unusual properties, including the diamond planet hypothesis. Several years ago, researchers proposed that Janssen might contain vast quantities of crystallized carbon in its interior. The idea emerged from density calculations and the star's carbon-rich composition. If true, Janssen's mantle could contain diamond layers hundreds of kilometers thick. Pressures and temperatures at those depths would force carbon into its densest crystalline form. The planet would literally be made partially of diamond. The hypothesis captured public imagination. Media reports dubbed it the Diamond Planet. But the reality is more complex and less certain. Recent observations suggest the magma ocean model better explains Janssen's observed properties. A diamond-rich interior remains possible but hasn't been confirmed. The planet's true composition likely lies somewhere between pure diamond and pure silicate rock, with carbon playing a significant but not dominant role. What we know for certain is that Jansen's discovery path was messy. The planet was first detected using radial velocity measurements, which tracked the star's subtle motion caused by orbiting planets. Early analysis suggested a planet with a 2.8-day orbital period. For several years, astronomers accepted this interpretation. Then Jack Wisdom reanalyzed the data in 2005. He argued the 2.8-day signal was an alias, a mathematical artifact created by combining the true orbital period with the observing schedule. He suggested the real period might be different. Other researchers published analyses supporting the 2.8-day planet. The debate continued. In 2010, Rebecca Dawson and Daniel Fabrici solved the puzzle. They demonstrated conclusively that the true orbital period was 0.7365 days, less than 18 hours. The 2.8-day signal was indeed an alias. This correction fundamentally changed our understanding of the planet. It moved Jansen from very close to extraordinarily close. The difference matters enormously when considering surface conditions and atmospheric survival. The transit discovery in 2011 confirmed the corrected orbital period. The MOST Space Telescope monitored 55 Cancri continuously for 2 weeks, capturing multiple transits exactly when Dawson and Fabrici's analysis predicted. Transit observations measure a planet's size by recording how much starlight it blocks. Combined with mass from radial velocity, this gives density. Density reveals composition. Jansen's density indicates it's rocky, not gaseous. But the exact internal structure remains debated. Is there a diamond layer? How thick is the magma ocean? Does a solid core exist beneath the molten mantle? These questions await better data. Temperature measurements added another layer of mystery. Spitzer Space Telescope observations in 2013 mapped Jansen's thermal emission using infrared light. The results showed something unexpected. The hottest point on the planet's day side was offset from the substellar point, the location directly facing the star. Instead of maximum temperature at the center of the day side, the hottest spot was shifted about 30 to 40 degrees eastward. Why? Something must be transporting heat across the surface. On a tidally locked world with no atmosphere, the hottest point should be directly under the star. The offset indicates active heat redistribution. Atmospheric winds could explain it. But at the time, scientists weren't sure Jansen had an atmosphere. Another possibility involved the planet's rotation. Tidal locking isn't always perfect. Some planets maintain slight rotational drift, which could shift the hottest spot. Or perhaps internal convection creates asymmetric heat flow that affects surface temperatures. The puzzle deepened when observations showed temporal variability. Jansen's thermal emission changed between different observing sessions. Sometimes it appeared brighter, sometimes dimmer. The variations were too large to be measurement noise. Something on or around the planet was changing. One explanation involves massive volcanic eruptions. If Jansen experiences supervolcanism, eruptions that dwarf anything on Earth, they could inject enormous dust clouds into the atmosphere. These clouds would temporarily block thermal emission, making the planet appear cooler. As the dust settled or dispersed, brightness would return to normal. Repeated eruptions would create the observed variability. Another hypothesis suggests a gas torus co-orbiting with Jansen. Picture a donut-shaped cloud of material surrounding the planet's orbit. Similar structures exist in our solar system. Jupiter's moon Io produces a plasma torus from its volcanic emissions. If Janssen continuously vents gas from its surface, some might remain in orbit around the star, creating a variable cloud that occasionally obscures the planet. These mysteries motivated the James Webb Space Telescope observations. Webb's unprecedented sensitivity and spectral resolution offered a chance to settle fundamental questions. Does Janssen have a real atmosphere? What is it made of? How does it survive? The observing campaign required meticulous planning. Webb observed the system from multiple complete orbits. Each observation lasted about 8 hours, nearly half of Janssen's orbital period. The telescope captured infrared light from the system both when the planet was visible beside the star and when it passed behind the star during secondary eclipse. Secondary eclipse occurs when the planet moves behind the star from our perspective. During eclipse, we see only starlight. Before and after eclipse, we see the combined light from both star and planet. Subtracting the eclipse measurement from the combined measurement isolates the planet's thermal emission. This technique is called secondary eclipse spectroscopy. The precision required is extraordinary. Janssen's thermal emission is thousands of times fainter than the star. Measuring it means detecting a tiny brightness change against an overwhelming background. Webb's instruments, NIRCam and MIRI, work at different infrared wavelengths. NIRCam covers 4 to 5 microns. MIRI extends from 5 to 12 microns. Together they provide a continuous spectrum showing how much light the planet emits at each wavelength. That spectrum reveals composition. Different molecules absorb and emit light at characteristic wavelengths. Carbon dioxide has a distinctive absorption feature around 4 to 5 microns. Carbon monoxide shows different patterns. Vaporized rock elements like silicon and iron would create yet another spectral signature. When the team analyzed Webb's data, they saw clear evidence for carbon-bearing gases. The spectrum showed reduced brightness between 4 and 5 microns, exactly where carbon dioxide and carbon monoxide absorb light. The signature didn't match vaporized rock. It matched volatile gases. This was the breakthrough. After years of debate, Webb provided definitive evidence that Janssen has a real atmosphere composed of actual gases, not just rock vapor. The atmosphere is likely dominated by carbon dioxide or carbon monoxide, probably both. These gases are continuously supplied by volcanic outgassing from the magma ocean below. The discovery settles one question but raises others. How thick is this atmosphere? How does its pressure compare to Earth's or Venus's? Does composition vary between dayside and nightside? Are there other gases present in smaller quantities? What about clouds or haze? Some answers will come from additional Webb observations. Others require different techniques. Future missions might directly image the planet, separating its light from the stars without relying on eclipses. Spectroscopy at higher resolution could detect trace gases and measure isotope ratios, revealing details about the atmosphere's chemistry and evolution. But the fundamental mystery is solved. Janssen has an atmosphere against all expectations. It survives in conditions that should strip it away within thousands of years. The magma ocean continuously replenishes lost gases, maintaining equilibrium between outgassing and escape. This mechanism allows the atmosphere to persist for billions of years despite hostile conditions. The implications extend far beyond one planet. If atmospheres can survive on worlds as extreme as Janssen, where else might they persist? What about planets slightly farther from their stars, where conditions are less hostile? Could super-Earths in intermediate environments maintain thick atmospheres for geological timescales? What does this mean for habitability across the galaxy? The discovery opens doors to understanding atmospheric evolution across the galaxy. Rocky planets exist in every configuration imaginable. Some orbit close like Janssen. Others circle at comfortable distances. Many fall somewhere between. Each environment tests different survival mechanisms. Janssen proves that extreme proximity doesn't automatically mean atmospheric death. The magma ocean mechanism works. It maintains equilibrium between loss and replenishment. But does this mechanism scale? Could slightly cooler worlds with less volcanic activity still maintain atmospheres through similar processes? What about planets around different types of stars? Red dwarfs are smaller and cooler than our Sun, but they emit powerful stellar flares that could strip atmospheres more efficiently than steady radiation. Do magma ocean planets around red dwarfs survive or succumb? These questions matter because red dwarfs make up roughly 70% of all stars in the galaxy. If their planets can't maintain atmospheres, that dramatically narrows the search for habitable worlds. Conversely, if Janssen's mechanism works around red dwarfs too, billions of additional worlds might retain atmospheres despite hostile conditions. The connection to Earth's past runs deeper than surface similarities. 4 billion years ago, our planet was a hellscape. Continuous asteroid bombardment kept the surface molten. The atmosphere was thick with carbon dioxide, water vapor, and other volcanic gases. No oxygen existed. No ozone layer protected the surface from radiation. Life had not yet emerged, or if it had, it clung to the most extreme refuges imaginable. That early Earth resembled Janssen in many ways. Not in temperature, Earth was cooler. But in the fundamental process of atmosphere formation through volcanic outgassing from a magma-covered world. Studying Janssen lets us observe this process happening now, 41 light-years away, rather than trying to reconstruct it from geological clues billions of years old. The insights apply to Venus too. Our sister planet may have started with oceans and a temperate climate. Runaway greenhouse warming turned it into an inferno with surface temperatures exceeding 860 degrees Fahrenheit. Venus today has a crushing carbon dioxide atmosphere 90 times thicker than Earth's. That atmosphere likely formed through volcanic outgassing, similar to the mechanism sustaining Janssen. Understanding how magma ocean worlds generate and maintain atmospheres helps explain Venus's transformation. It might even reveal whether Venus could have remained habitable if certain conditions had been different. Mars presents a contrasting case. The red planet once had a thicker atmosphere and liquid water on its surface. Rivers carved channels. Lakes filled impact craters. The atmosphere was dense enough to support a water cycle. Then Mars lost most of its atmosphere to space. Without a strong magnetic field to deflect the solar wind, atmospheric gases were gradually stripped away over hundreds of millions of years. Today Mars has only a thin carbon dioxide atmosphere, about 1% the density of Earth's. Janssen's survival mechanism, continuous volcanic replenishment, is precisely what Mars lacked. Once Martian volcanism declined, the atmosphere couldn't be replenished fast enough to compensate for losses. The planet dried out and froze. Comparing these worlds reveals the delicate balance required for atmospheric persistence. Too little volcanic activity means gradual loss. Too much stellar radiation accelerates escape. A magnetic field helps but isn't always necessary if replenishment rates are high enough. Janssen demonstrates that extreme volcanism can compensate for extreme radiation, maintaining atmosphere despite lacking magnetic protection. The search for habitable worlds depends on understanding these boundaries. The habitable zone around a star is traditionally defined as the region where liquid water can exist on a planet's surface. Too close and water boils away. Too far and it freezes. But habitability requires more than temperature. It demands atmospheric stability over geological timescales. A planet in a habitable zone means nothing if it can't hold on to its atmosphere. Janssen teaches us that atmosphere retention is complex. It's not just about distance from the star or planetary mass. Volcanic activity, stellar radiation, magnetic fields, and internal heat all interact. Some planets in the habitable zone might lose their atmospheres. Others outside it might keep theirs through vigorous outgassing. The traditional habitable zone concept may be too simplistic. We need a more nuanced understanding that accounts for atmospheric dynamics, not just surface temperature. Future observations will refine our knowledge of Janssen's atmosphere. Webb can observe the planet again, measuring how its spectrum changes over time. Variability would indicate weather patterns, volcanic events, or atmospheric circulation. Long-term monitoring could reveal seasonal changes if the planet's orbit is slightly elliptical, though current evidence suggests it's nearly circular. Other instruments could contribute different perspectives. Radio telescopes might detect emissions from atmospheric chemistry. Optical telescopes could measure reflected starlight, revealing cloud properties or atmospheric hazes. Each observation adds another piece to the puzzle. The goal is building a complete atmospheric model: temperature structure, pressure profile, chemical composition, circulation patterns. That model would be the first comprehensive picture of a rocky exoplanet atmosphere. Beyond Janssen, dozens of other rocky exoplanets await similar scrutiny. Many orbit closer to their stars than Mercury does to our Sun. Some are larger than Earth but smaller than Neptune, occupying a size range with no solar system equivalent. These super-Earths and mini-Neptunes are common in the galaxy, yet we understand them poorly because we lack local examples. Do they have atmospheres? What are those atmospheres made of? How thick are they? Can they support liquid water despite high temperatures? Janssen provides a template for answering these questions. The techniques developed to study it, secondary eclipse spectroscopy, thermal phase curves, long-term monitoring, apply to other worlds. Each new observation expands our catalog of atmospheric types. Rocky planets with hydrogen atmospheres. Worlds with water vapor envelopes. Planets surrounded by carbon monoxide. The diversity is likely enormous, limited only by the laws of chemistry and physics. The technology enabling these discoveries barely existed a decade ago. Webb launched in late 2021. Its predecessors, Hubble, Spitzer, Kepler, laid groundwork but lacked the sensitivity and spectral resolution for rocky planet atmospheres. Webb's mirror is nearly 3 times wider than Hubble's, collecting much more light. Its infrared instruments operate at wavelengths ideal for thermal emission spectroscopy. And its position at the second Lagrange point, 1 million miles from Earth, provides a stable environment free from atmospheric interference. These advantages combine to make observations like Janssen's possible. Without Webb, we'd still be debating whether rocky exoplanet atmospheres could be detected at all. Now we know they can. The question shifts from whether to how many and what types. Next-generation instruments will push further. Ground-based telescopes with adaptive optics systems that compensate for atmospheric distortion are reaching unprecedented precision. Space missions under development target rocky planets specifically. Some will use star shades, giant structures flying separately from telescopes to block starlight, making planets visible. Others will employ coronagraphs, internal masks that achieve similar blocking. These techniques enable direct imaging rather than relying on transits or eclipses. Direct imaging reveals more detail, including atmospheric composition, cloud patterns, and surface features if resolution permits. The ultimate goal is finding another Earth. A rocky planet in a habitable zone with an atmosphere containing oxygen, water vapor, and other biosignatures. Life as we know it requires liquid water and produces oxygen through photosynthesis. Detecting both in an exoplanet atmosphere would strongly suggest biology. Janssen isn't that world. It's too hot, too hostile, too extreme. But every planet we study teaches us something about planetary diversity and atmospheric resilience. Janssen proves that atmospheres can survive in conditions once thought impossible. That expands the parameter space where we might find habitable worlds. If atmospheres persist around planets as extreme as Janssen, they might exist in many environments we haven't fully considered. The galaxy may be richer in atmospheric diversity than we imagined, with implications for where life might arise and endure. Standing back, the Janssen story reflects humanity's expanding vision. 40 years ago, we didn't know whether planets existed around other stars. The first exoplanet discovery came in 1992, orbiting a pulsar. The first around a sun-like star came in 1995. Now we know thousands of exoplanets, with more discovered every year. We've progressed from merely finding planets to characterizing their masses, sizes, orbits, and now atmospheres. Each advance reveals the universe in greater detail. Janssen represents the cutting edge of this progression, a world so alien yet so important for understanding how planets work. Its magma oceans, carbon-rich atmosphere, and extreme temperatures challenge our assumptions and expand our knowledge. In 41 years, light from Janssen reaches Earth, carrying information about a world that shouldn't exist by old rules but does by new understanding. That light, captured by our most sophisticated instruments, tells a story of resilience, complexity, and the endless capacity of nature to surprise us. The Janssen discovery arrives at a turning point in our understanding of what planets can be. For centuries, we built theories from 8 local examples. Mercury through Neptune. A handful of moons. 1 asteroid belt. Limited data breeding limited imagination. Then exoplanets shattered those constraints, revealing worlds that defy every category we'd constructed. Hot Jupiters orbiting closer than Mercury. Super-Earths with no solar system equivalent. Planets around binary stars, around pulsars, in configurations our models never predicted. Janssen sits at the extreme end of this spectrum. A world where rock boils. Where atmospheres persist through mechanisms we're only beginning to grasp. Where every measurement contradicts what textbooks said was possible. It's not just another data point. It's a fundamental challenge to planetary science orthodoxy. The implications ripple outward in unexpected directions. Consider the habitable zone concept. We've spent decades refining estimates of where liquid water can exist around different stellar types. But if atmospheric retention depends on volcanic vigor as much as stellar distance, those calculations need revision. A planet outside the habitable zone might maintain temperate surface conditions through internal heat and thick atmosphere. One inside might lose its air despite comfortable temperatures. Janssen proves the old boundaries were too rigid. Atmospheres survive where theory said they couldn't. Magma oceans sustain themselves for billions of years through tidal heating. Carbon dioxide and carbon monoxide circulate in environments hot enough to vaporize iron. The universe operates by different rules than we assumed, and each discovery reveals another layer of complexity we'd missed. The technological achievement deserves recognition too. Webb's instruments detected molecular absorption features in thermal emission from a rocky planet smaller than Neptune, orbiting a sun-like star 41 light-years away. The planet's contribution to total system brightness is infinitesimal. Yet Webb teased apart that faint signal, measured it across multiple wavelengths, and identified specific chemicals in an alien atmosphere. 20 years ago, this would have seemed impossible. 10 years ago, it was theoretical. Now it's routine. That progress accelerates. Webb will observe more rocky exoplanets, building a catalog of atmospheric types. Ground telescopes with 30-meter mirrors are under construction, capable of even finer measurements. Space missions in planning stages will directly image Earth-sized worlds around nearby stars. Within the next decade or two, we'll have spectroscopic data from dozens of rocky planets across a range of environments. Janssen is the first clear detection, but it won't be the last. Each atmosphere tells a story about planetary evolution. How did this world form? What was its early environment? Has its atmosphere changed over time? Is volcanic activity increasing or declining? These questions connect to the broader narrative of how planetary systems develop from protoplanetary disks into mature configurations. Janssen's carbon-rich atmosphere might reflect the unusual composition of its parent disk. Other planets will show different chemistries, revealing different formation histories. The connection to Earth's past grows stronger as we learn more. Our planet spent hundreds of millions of years as a magma ocean world. That phase determined what atmosphere we started with, which influenced how the surface eventually solidified and cooled. Water vapor condensing into oceans. Carbon dioxide dissolving into seawater. Nitrogen accumulating because it's chemically inert. These processes set the stage for everything that followed, including the emergence of life. We can't observe Earth 4 billion years ago. Those rocks are gone, subducted or eroded beyond recognition. But we can observe Janssen now, watching processes that mirror Earth's infancy. The magma ocean convection. The volcanic outgassing. The atmospheric chemistry under extreme conditions. It's a living laboratory for planetary formation, preserved by circumstances that prevent it from moving to the next evolutionary stage. Venus offers another parallel. The runaway greenhouse effect that created its hellish surface may have started from conditions similar to early Earth. Small differences in initial water content, volcanic activity, or atmospheric composition could determine whether a planet becomes habitable Earth or scorched Venus. Understanding how atmospheres form and persist on magma ocean worlds helps identify which factors matter most. That knowledge applies to every rocky planet in every system. Mars shows the opposite extreme. A world that lost its atmosphere because volcanic replenishment couldn't match escape rates. Janssen demonstrates that vigorous outgassing can maintain atmosphere despite extreme radiation. Mars lacked that vigor. Its smaller size meant faster interior cooling. Volcanism declined. The atmosphere thinned. Today we see the end result, a frozen desert with only wisps of air remaining. These comparisons reveal that atmospheric evolution isn't deterministic. Similar planets can follow divergent paths depending on subtle variations in initial conditions and subsequent history. Some retain thick atmospheres for billions of years. Others lose them within hundreds of millions. The galaxy likely contains examples of every intermediate state, each frozen at a different point in the progression from formation to final configuration. Finding habitable worlds requires understanding these pathways. We need to identify which planets can maintain atmospheres long enough for life to emerge and evolve. That means looking beyond simple temperature calculations. Volcanic activity matters. Stellar radiation matters. Planetary mass and composition matter. Magnetic fields help but aren't always necessary. The interactions between these factors create outcomes we're only beginning to map. Janssen expands that map into territory we previously marked as impossible. Atmospheres in extreme radiation environments. Magma ocean worlds maintaining volatile envelopes through continuous outgassing. Carbon-bearing gases surviving at temperatures that vaporize rock. Each observation adds nuance to our understanding of what's possible, pushing the boundaries of known atmospheric physics. The search continues with renewed purpose. Thousands of exoplanets await detailed characterization. Many are rocky. Many orbit in or near habitable zones. Some may harbor atmospheres with biosignatures, oxygen, methane, combinations of gases that suggest biological activity. Finding those signatures requires the techniques pioneered on worlds like Janssen. Secondary eclipse spectroscopy. Thermal phase curves. Long-term monitoring for variability. Future discoveries will surprise us. They always do. Each planet studied reveals unexpected features, challenges assumptions, forces theoretical revisions. Janssen challenged the assumption that rocky planets this close to their stars can't have atmospheres. What will the next discovery challenge? Perhaps we'll find atmospheric oxygen on a lifeless world, produced through non-biological chemistry. Or detect complex organic molecules in places we thought too extreme for chemistry to occur. Or discover that magnetic fields play different roles than we believed. The universe doesn't care what we think is possible. It operates according to physical laws, and those laws permit configurations we haven't imagined yet. Our job is observation, measurement, analysis. Build instruments sensitive enough to detect faint signals. Develop techniques clever enough to extract information from noise. Construct models flexible enough to accommodate new data without breaking. Janssen succeeds because it exists in a narrow parameter space where multiple extreme conditions align. Large enough to stay geologically active. Close enough to maintain surface melting. Tidally locked to create hemispheric extremes. Compositionally suited to supply carbon gases through outgassing. Change any variable and you get a different outcome. But in this exact configuration, the result is a magma ocean world with a carbon-rich atmosphere surviving against impossible odds. That survival teaches humility. Our theories predicted atmospheric loss would dominate. They were wrong. Nature found a mechanism we'd underestimated: continuous volcanic replenishment maintaining equilibrium with escape processes. The mechanism was there all along, operating on early Earth, on early Venus, on countless worlds across the galaxy. We just needed precise enough observations to confirm it. The James Webb Space Telescope provided those observations. Its infrared capabilities, its spectral resolution, its exquisite sensitivity combined to detect molecular absorption features in a rocky exoplanet atmosphere. The first clear detection of its kind. A milestone in exoplanet science. Proof that we can characterize rocky planet atmospheres despite their faintness and their distance. More milestones await. Direct imaging of Earth-sized worlds. Detection of water vapor on temperate planets. Identification of biosignatures in exoplanet atmospheres. Each achievement builds on previous ones, using techniques refined through observations like Janssen. The progression continues, limited mainly by technology and funding. As instruments improve, so does our ability to study ever more challenging targets. 41 light-years separates us from Janssen. Light traveling at 186,000 miles per second takes 41 years to cross that gulf. The photons Webb detected left Janssen in 1983, carrying information encoded in their wavelengths about a world that defies expectations. Those photons journeyed through interstellar space, arrived at our solar system, and entered Webb's optics to be recorded and analyzed. The information they carried changed our understanding of planetary atmospheres. Not through dramatic revelation, but through precise measurement of subtle spectral features. Science advances through exactly this process. Careful observation, rigorous analysis, gradual accumulation of evidence, occasional surprises that force theoretical revisions. Janssen delivered one of those surprises. A rocky planet with an atmosphere in conditions that shouldn't permit one. The discovery proves that atmospheric science still has fundamental lessons to learn. Our models are incomplete. Our assumptions sometimes wrong. The universe more diverse than our limited sample suggested. That diversity is what makes exoplanet science compelling. Every world is an experiment in planetary physics. Different initial conditions. Different evolutionary paths. Different outcomes. Some produce Earths, temperate, wet, potentially habitable. Others become Venuses, scorched, hostile, shrouded in crushing atmospheres. Still others turn into Mars analogs, cold, dry, stripped of most air. And some become Janssens, extreme, unexpected, challenging everything we thought we knew. The galaxy contains hundreds of billions of stars. Most have planets. Rocky worlds number in the billions. Each one represents a unique combination of formation history, composition, stellar environment, and evolutionary trajectory. We've characterized perhaps a few dozen in detail. The sample is tiny. The lessons preliminary. But each observation adds to our knowledge, building toward comprehensive understanding of how planets work. Janssen's contribution to that understanding is clear. Atmospheres can survive extreme radiation through continuous volcanic replenishment. Magma ocean worlds maintain carbon-rich envelopes despite surface temperatures exceeding 6,000 degrees Fahrenheit. Tidally locked planets redistribute heat through atmospheric circulation even when that atmosphere shouldn't exist according to old theory. These aren't minor details, they're fundamental insights about planetary atmospheric physics. The knowledge applies beyond Janssen. Every ultra-hot rocky planet. Every tidally locked world. Every planet with active volcanism and strong stellar radiation. The mechanisms we've identified operate wherever similar conditions exist. That means potentially thousands of worlds across the galaxy, each maintaining atmospheres through processes we're only now beginning to understand. Looking forward, the questions multiply faster than answers. How common are magma ocean planets? Do they exist around different stellar types? Can slightly cooler versions maintain atmospheres through similar mechanisms? What about planets with different compositions, more water, less carbon, varying amounts of metals? How do magnetic fields influence atmospheric retention when volcanic activity is vigorous? Do some planets transition from magma ocean states to solid surfaces, and if so, how does that affect their atmospheres? Each question requires observations. More Webb time. Future missions. continued monitoring of known worlds and characterization of newly discovered ones. The work spans decades, involves hundreds of scientists, demands billions in funding. But the payoff is understanding our place in the universe. Learning how common Earth-like worlds are. Discovering whether life exists elsewhere. Finding out if our planet's history is typical or exceptional. Jansen moves us one step closer to those answers. Not through being Earth-like, it's about as far from Earth as a rocky planet can get. But through demonstrating that planets operate under a wider range of conditions than we believed possible. If atmospheres survive at Jansen's orbital distance, they might persist in many environments we'd written off as too hostile. That expands the search space for habitable worlds and increases the odds that we'll eventually find one. The universe is vast. The number of planets staggering. Most will remain forever beyond our ability to study in detail. But the ones we can observe teach us principles that apply to all the others. Physical laws operate the same everywhere. The chemistry of planetary formation follows universal rules. Atmospheric physics doesn't change based on location. So every planet we characterize tells us something about countless others we'll never see. Jansen tells us that nature is more resourceful than our models predicted. That equilibrium can exist between opposing processes even under extreme conditions. That volcanic vigor can maintain atmospheres despite powerful escape mechanisms. These lessons apply to exoplanets we'll discover next year, next decade, next century. They become part of the framework we use to understand all rocky worlds. 41 light-years away, Jansen continues its 18-hour orbit. The magma ocean churns. Volcanic gases bubble to the surface. Stellar radiation strips away atmosphere as fast as outgassing replenishes it. The process has continued for billions of years and will continue for billions more. We've observed it for a few years at most. But those observations revealed something we'd never have predicted from theory alone. A world that shouldn't exist by old rules but does according to new understanding. That's how science progresses, one impossible planet at a time.